In this video, we will study about PN junction diode. What is a PN junction diode? PN junction diode is a semiconductor device which is used to pass the current in a single direction. What does it mean? It means that if I allow the current in some device, suppose this is that one, if I allow the current to pass in this direction and I am successful in passing the current, but when I reverse the polarity, then in this direction there is no current. So such a device, semiconductor device, is known as diode.
Direction of the arrow represents the direction of current in the diode.
A PN junction diode is made by combination of P-type semiconductor and N-type semiconductor under a complex process. And after buffering N-type semiconductor over the surface of P-type semiconductor, a metal plates are connected at both ends, and with that metal the two terminals, these are the terminals, are connected. Thus a PN junction diode is formed, and this is the symbol of PN junction diode. This triangular portion of the symbol represents the P region or P-type semiconductor, and this vertical line represents the N-type semiconductor. Now, before starting the working of PN junction diode, let's see what happens when a P-type semiconductor and N-type semiconductor are combined to form a diode. When a P-type semiconductor is joined with the N-type semiconductor to form a PN junction diode, of course under a complex process, then what happens actually? There establishes a junction. So this dotted line is representing the junction of the diode. On the one side of the junction, this is the P-type semiconductor, and on the another side of the junction, this is the N-type semiconductor. And just you recall, when we were studying about the P-type and N-type extrinsic semiconductors, then we come to know in this type of semiconductor, the majority current carriers are holes and the minority current carriers are electrons. That is, number density of holes is greater than the number density of electrons in P-type semiconductor. Whereas in N-type semiconductor, the majority current carriers are electrons and the minority current carriers are holes. That is, number density of electrons is more than the number density of holes in N-type semiconductor. We see that the concentration of holes in the P region is more than the concentration of holes in the N region. And the concentration of electrons in the N region is more than the concentration of electrons in the P region. And due to this concentration difference, I must use a technical term, concentration gradient. There is a concentration gradient of holes as well as of electrons. Means there is a concentration difference in these two regions for holes as well as electrons. And due to this difference in the concentration, there will set up a flow, set up a current that is called diffusion current. Means the diffusion of holes will start from P region to N region, as well as diffusion of electrons will start from N region to P region. Because the diffusion always take place from high concentration to low concentration. So if I take the example of holes, So the holes will start diffusing in this direction, and therefore there will be a current I will call diffusion current of the holes. Whereas the diffusion of electrons will take from N region to P region, and so this will be the direction of current of electron due to the diffusion, and I will call it diffusion current of electron. Now, just you recall the concept of doping. In the p-type semiconductor, the dopant you had used indium 13th group, and in the N region you had used a dopant of 15th group, for example phosphorus. So these current carriers are generally obtained from these dopants, that is, these electrons are due to the doping of phosphorus and these holes are due to the doping of indium. Just you see, in the last video I had discussed this indium is providing the hole in the lattice of pure semiconductor to form an extrinsic semiconductor of category P type, and when this indium receives the electron from anywhere, so this indium converts into the negative core. So the dopant of this region will convert into a negative core. So these holes, after receiving the electron, just you see the diffusion of electron is taking in this side from here to here. So when these electrons will move to this indium, these holes, so holes will occupy these electrons, and these electrons will be known as immobile negative charge. Actually, these electrons which are appearing here are the negative indium cores, core of indium. To know about the core of indium, negative core, just you watch the previous video, Semiconductor part 3. Just you watch, there I have explained how this indium converts into the negative core. Similarly, when these holes are diffusing to the N region in this side, so these holes will come here with the phosphorus, or you can say when these electrons have moved to this region, so this phosphorus has been converted into the positive core. So here near the junction a positive core will be left, that is immobile positive charge. Thus finally what we can say, because of these diffusion currents near the junction, the immobile charges are the negative core and positive core on the either side of the junction are being deposited. So due to the deposition of these immobile charges near the junction, an electric field will set. Just you see, in this region, in the N type of semiconductor, there has been a positive immobile charge, and in the P region of the semiconductor or P region of the diode, a negative immobile charge has been accumulated. Because of that, an electric field in this direction from positive to negative in this diode will be developed across the junction. As and when this electric field is developed, now this electric field start applying force on these current carriers, holes and the electrons of both the sides. And we know that the electric field apply the force on the electron in the opposite direction, whereas on the positive charges in the same direction of the electric field. That's why there will be a force on these holes due to the existence of this electric field in this direction. So the holes will start drifting in this direction, and because of that there will be a drift current of the holes, drift current. And also this electric field will start applying force on the electrons in the opposite direction of electric field. So the electric field will apply the force on this electron. This is the electron negative sign I have written. So the electrons will start drifting in the opposite direction. And so there will be a current of electron because of the drift. I will call drift current of the electrons. So what we see here, when the time passes, by the time, this drift current will be equal to the diffusion current. Means at equilibrium, this drift current and diffusion current both become equal. This drift current and diffusion current both become equal. Means we will say that now the diode is in equilibrium. And this region where these positive and negative charges are stored, are accumulated and have produced the enough electric field so that the drift current value and the diffusion current value is equal but in opposite, producing the net current 0. That is, we can say the further diffusion and the drift is stopped. The further diffusion and the drift of current carriers is stopped. So this region is known as depletion layer. Because of its character, its name has been given depletion layer. Because this is the layer of immobile charges due to which the net current, or you can say the drift current as well as the diffusion current in the diode becomes 0. And now, when the depletion layer is set up, it stops the flow of current. So how you will write about the depletion layer? So in a very simple language, just you write the depletion layer is the region across the junction of diode due to the accumulation of immobile charges, which stops the further diffusion and the drift of current carriers. So that's simple. Okay. Now we have studied in the second chapter that if there is electric field, just to recall the second chapter, and here there are the 2 points. So we have studied a relation dV equals to minus E dot dr. This relation says that in the direction of electric field potential decreases, means if there is a potential V1 and here there is a potential V2, so V1 will be greater than V2. Overall, there is a potential difference. Okay. So here also, if in the depletion layer across the junction in your diode there is electric field, so there will be a potential difference. And this potential difference V equals to E is the electric field and D is the width of depletion layer. So this is the potential difference across the depletion layer. And what is the role of depletion layer? Depletion layer has stopped the current, stopped the drift and the diffusion of current carriers. Because of that, this potential difference across the depletion layer is known as barrier potential. We call it barrier potential, or we call it barrier height as well. Barrier height. When the width of depletion layer will increase due to some circumstances, then your barrier potential will increase. And when the width of depletion layer will decrease because of some circumstances, then the barrier potential will decrease. Just you see the name barrier. When the barrier will decrease, we can think the current carrier will start crossing the junction and the current will start passing through the diode. That's why this study of barrier potential is very important. Now, what you will write and how you will write about the barrier potential? So, the barrier potential is the potential difference across the junction in the depletion layer due to which the current carriers cannot cross the junction and the current is zero. That is called barrier potential. How you will calculate? You need to know the electric field. So the value of electric field which has been developed because of the accumulation of these immobile charges is written as sigma upon epsilon naught. Sigma is the surface charge density in this region and in this region. So overall, in this diode, when a PN junction diode is formed, so as and when the diode is formed, instantly a depletion layer is developed, a barrier potential is developed. And now in the diode, the net current is zero. So finally, now we will discuss what should we do so that the current start passing through the diode. And connecting a diode with some source to pass the current is known as biasing of diode. Is known as biasing of diode, means connection of diode with some battery or some sources. That connection is called biasing of diode. So now we will study what are type of the biasing and how a diode is connected or how a diode is biased.